welcome. So, this is week number 5, and in this week we are going to talk about digital control design, and we will start with design based on continuous time model. And to understand various transformation in terms of S to Z domain, in this lecture we are particularly focusing on various continuous time to discrete time conversion methods. So, in this lecture we will first talk about continuous time to discrete time transformation methods, what are their stability under different transformation, and then summary of this transformation methods. So, we will start with discrete time control system. If you want to design via transform method, what are the methods that are available? One is the backward difference, another is the forward difference, another is the bilinear transformation, then step invariance method, math pole 0 and numerical. So, first three methods are numerical integration method. And also under bilinear transformation, sometimes people talk about frequency pre-warping. So, in this lecture we want to first show first three different methods, how they are coming and how accurate as well as what is the implication in stability. So, we will start with a pure integral control in continuous time, and we are taking an error voltage VET and it is passed through an integral controller with an analog integral gain, that means KIC, which our continuous time integral gain, and consisting of pure integrator. And we can write the time domain expression ui of t KIC into 0 to t VET. So, we are trying to integrate over time 0 to the current time. Now, in order to achieve an analogous discrete time integral action, first we have to draw the sample and hold. So, in digital control, this error voltage passed through a sample and hold circuit, and this is a sample voltage, error voltage. And now, as if it passed through an equivalent or passed through a digital integral controller or discrete time integral controller, and then we are getting ui of sample t, that means sample ui of t. So, u star t is a sample version of this, and we want to get this transfer function between u sample to this error, and we want to show how they are compared with their continuous time counterpart. So, if we sample, then error voltage, which is v of t, we are sampling at every edge of the sampling clock with a time period of Ts. So, if you take at kth edge, there will be kTs, and that is represented by Vek, which is nothing but the sample value of the error voltage at t equal to kTs, that means at the kth edge of the sampling clock. Now, let us consider an error voltage profile. So, this is an arbitrary profile that we have considered, which is shown here, V error voltage, and if we want to find the integration of the error voltage, that means we are trying to compute the integration of the error voltage during the duration 0 to nTs. That means, if we take a pure analog control and if we want to get this integration from 0 to nTs, where Ts is the sampling time. Right now, we are not sampling. So, you want to compute the total. Suppose we are taking 100 of Ts, that means after 0 to Ts, Ts to 2 Ts, like that, we will wait till 100 Ts and we want to integrate. So, then we know the expression, it will be 0 to nTs. Then if we further break down, so that means if you consider this integration, that means let us say we are talking about maybe somewhere here we will get 100, or maybe we are talking about nTs, that means somewhere here there will be nTs. So, we want to find the area under this curve till this nTs time. How can you obtain? We can obtain this by breaking this into pieces. That means, we can take this first, any of this segment, we can take any of this segment, let us say we are taking this segment, we are taking, so we are talking about this particular segment, okay. So, this particular segment we are talking about, we want to get. What is this segment integration? We are representing ik of tau and where tau is varying from k minus 1 Ts to k Ts, and this is exactly what we represent the ik. So, we can break, that means we can sum up if we take this window, that means the sampling window interval, and if we take the area under the curve, and for each of this segment if you sum them, then you will get this complete integration. And this particular block we are representing integration I k tau, which is nothing but integration k minus 1 Ts to k Ts v e tau d tau, and that we are denoting as I k tau. Okay. Now, we want to find this, and that means we want to find this exact integration, but if we sample it, then we will only have the sample information. That means for the digital control or maybe for A to D converter or sampler, after sample and hold block, we will only have this information, that means sample then hold, sample then hold, but we will not have any information inside this, that means we will not have any information in between two samples. So, we need to find the area, we need to approximate this area under the curve using available sample, because we are not talking about a continuous time error signal, we are talking about a sample error signal, and we need to approximate, we want to approximate the continuous time integration by means of sample quantity. So, first method, option 1, if we take this sample and then we using this sample we approximate, that means it will be constant for this cycle. For example, when as per this method we take this sample and then we take this area under the curve, that means in this case I k tau can be approximated to be v e k, which is this sample value into Ts, and this method is known as backward Euler method. Option 2, we can also take this sample and find out this area under the curve, and you will find this will be v e k minus 1, which is here into Ts, and that is known as forward Euler method. Also, we can get another way, we take both the sample information, which is v e k minus 1, and this sample is our v e k, then we get the mid value of this and approximate using this particular area under the curve. And then if you get this area under the curve, first of all this mid value will be sum of these two divided by 2, and then you can approximate by this value, and this is known as Tustin method or bilinear transformation. Now, in the first method, if we want to get an integration, that means u I of n, the n value during 1 to n, what can we write? That means we are trying to get, that means we are trying to get what? T s to n T s, we are trying to get as if it is shown, and as if we are writing this tau into d tau, and there is a k I c term that we want to find out. So, this can be found by this this method. We have not used what is v k, that means this is the method, and here k I, that means we have taken T s out here. If we take, then this k I will be k I c into T s. Now, we want to approximate this, that means we want to find u of I. So, this is like Euler method, because if you take any kth interval, that means k minus 1 T s to k T s, we know that using backward difference method we are taking the right side of the sample. So, it is, that means we have to simply sum it, but if you continue to sum it, actually using method 1 we are doing, sorry, this interval should be 0 to T s, it should be 0 to T s because we are using backward method. So, even for 0 to T s this cycle, if we take using this backward method, we are getting v e T s into T s. So, this is the backward Euler method. So, for some For 0 to n ts, it will go up to k, because it will take the first sample at the end of the 0 to ts, it will take the end value, then n minus 1 ts to n ts, it will take the nth value. So, that is why this can be approximated. So, if you, but this you cannot implement, because this will be accumulated and it may saturate your storing element, because in digital control we generally use a memory block, so it will saturate. So, we need to use an incremental method or basically iterative method. So, here if you write this expression, that means if you write k equal to 1 to n V E k, this can be written as V, that means if this is denoted as V E n, for example, then we can get V E n to be V, because this sum, so V E, that sum. So, then we can get V E s equal to V E n minus 1, V E n minus 1 plus V E n. So, there is an iterative method, V E s sum. That means, let me write this integral once more. So, this is represented as V E s sum of this whole thing. Then we can write k 1 to n minus 1 V E k as V s n minus 1. So, then by iterative algorithm we can write V s of n equal to V s of n minus 1 plus V E n, that is it, and this iterative method we will be using to get this integral value. Okay? And then you can realize by inserting an unit delay, and if you obtain the transfer function by this method, you will get k I 1 by 1 minus z inverse. So, this is the integral transfer function using z domain, and this is using backward difference formula, backward difference method. Now, by the same method, if you go to forward difference, you see for the kth cycle, that means what is the forward difference method for k equal to, let us say 0 to ts. What is this in forward difference? It will be simply V E 0, we know that, right? Okay, because it is only taking between 0 to ts this value. And similarly, if we expand, that means if we expand the net duration, that means we are talking about the integration from 0 to n ts V E tau d tau. So, this can be represented by k equal to 0 to n minus 1, then it will be simply V of k into t, V of t. So, if we write, then it will be ts. So, this is using backward forward difference method. So, this is using forward difference method. And this method, if you again write in iterative algorithm, it will look like this. Okay, so you can implement this method by this transfer function, and if you obtain, this is the transfer function. Next, by bilinear transformation, the only difference is the last term, and here it will be replaced by the average of these two error, and that is written here. And if we obtain the implementation of this block, and if we find the transfer function, it will be k I by 2 z plus 1 by z minus 1. Now, if we want to map, that means a continuous time integration we started with, and we got a discrete time integration, and k I, the discrete time integral gain is this. What is f z? That means if we map s domain to z domain, for backward difference it will be z minus 1 by z, for forward difference z minus 1, and for bilinear transformation it will be z minus 1 by z plus 1. So, now we want to see the stability. If you use backward difference, and if you get z in terms of s. Now, we are talking about a s domain. This is my s plane, this is my sigma, and this is my j omega, we know. So, we can write s equal to sigma plus j omega, this is a standard term that we have written, and we replace this s expression here. Then what we will get? Z equal to this, and what we need for the stability in the z domain. So, this is in z plane, this is the real part and the imaginary part. So, it should be within the unit circle. That means, we need mod z should be smaller than unity, and that means if you take the mod of this function, it will come like this, and if you simplify, the requirement is this: 1 minus sigma whole square plus omega square should be greater than 1. Now, for the stable system in S plane, okay, and this is our real part sigma, we generally, for stable case, the sigma, that means sigma must be negative for the stable case, then 1 minus sigma whole square should be greater than 0 all the time, because sigma is negative. So, that means we can establish that this will be always, whether it is 0 or something else, this quantity is always greater than 0. So, we can maintain this condition. So, that will ensure that z will be always within the unit circle. That means, by this transformation method, a stable S plane pole will always be stable, but it is a conservative choice, because this will it will make sure it is stable, but it is a conservative choice. The forward difference, we know that z equal to s plus 1. Now, if we replace s equal to sigma plus j omega, then we will get z equal to 1 plus sigma plus j omega, and we need to ensure that z mod of z should be smaller than 1. And if you take the mod of this function, what we will get? That means, mod of this z means will be square root of 1 plus sigma whole square plus omega square, and the mod less than 1 means, if you take the square, it should be smaller than 1. And what does it indicate? Sigma and j omega, that means minus 1 is the radius, that means it is something like that, plus omega square, if we take equal to 1. So, this represents the equation of a circle with the center is minus 1 0, and that is exactly shown here, and with the radius of unity. So, it can only be stable in this transformation if we take any pole in this S plane inside this circle. That means because we know that for stability in the S plane, the real part should be have negative real part. That means, for actual stable plane, it takes the entire left hand side, but other than this shaded region outside, it will become unstable in the z domain. So, this transformation may lead to a stable pole, only shaded region can retain stability. Outside the stable region, in a stable S domain pole may become unstable in z domain. So, that is why the forward difference method must be avoided. The next is under bilinear transformation. If you write s equal to z minus 1 by z plus 1, and again if you simplify to write z in terms of s, now you write s equal to sigma plus j omega, and you replace and you rearrange, that means you obtain the z from here by substituting s in this expression, then you will get 1 plus sigma plus j omega, 1 minus sigma minus of j omega. And if you write in a complex number, because this is one complex number, let us say x, and this is another complex number, let us say y, and this polar representation of x and polar representation of y. So, you can take real part r1 by r2, then j. So, we want to make sure that the z mod of z should be smaller than 1. So, we are interested in the magnitude, we are not interested in the phase. So, we want to make sure that r1 by r2 must be smaller than 1. So, this will actually require this result. So, that means, if we again write what is my r1. So, if you take the first term, what is the r1 for this? So, here r1 will be 1 plus sigma whole square plus omega square. the square root. And what is my R2? It will be, it is coming from here, right. So, it will be 1 minus sigma whole square plus omega square. So, if you take R1 by R2, it will be 1 plus sigma whole square plus omega square divided by 1 minus sigma whole square. So, this must be smaller than 1, and if you write it here, that means if you simply square it, you need to satisfy this, and if you, so it will end up with sigma is less than unity. So, it requirement for, if you want to ensure that a stable z domain pole, then it requires the sigma should be negative, and that is exactly the requirement of any, that means if you take any s equal to sigma plus j omega, for stable s domain requirement the sigma must be negative and which is consistent. That means, in this method the stable pole in s domain will remain stable in the z domain. So, it will retain the stability of the continuous time, and the binary transformation it retain the stability. Now, we want to convert a PID controller from continuous time PID controller to discrete time. So, this is a continuous time ideal PID controller parallel form, and if we write in Laplace domain, it will be the function with 0 initial condition. Then discrete domain, if we use a backward difference formula, what will be our integral gain? I mean, we know that this term can be replaced by this term. Similarly, this term, similarly if you take this term, it will be replaced by this term, and this is, we are using backward difference formula. Then if you write this full form, we can separate two things. That means, if you take the inverse Laplace u of n, I want to write, yeah, it is written here, which is the inverse Laplace of this, it is coming from here. So, as if it is a PID controller, it has three components. One, the component due to the proportional action, the component due to the integral action, and the component due to the derivative action. What is u p of n? It will be simply Kp into Vcn. That means, there is a error which is common. This is my error signal which is common. What is I? We already know that under backward transformation, I mean difference formula, ui of n is nothing but ui of n minus 1 plus this term is nothing but discrete time integral gain, okay, and this is of course error. And then the derivative, it is nothing but the discrete time derivative gain, and KDC is the continuous time derivative gain by Ts, and it will be V error n minus V error n minus 1. So, this is the formulation. So, if you want to realize this ideal PID controller, so that means, if you first term is straightforward, it is simply going. The second term you have this 1 z in the delay term which is here in the feedback path, and the third term you need a delay and then subtraction. So, you need a delay, this is delayed input and then subtractor, then multiplied by this digital derivative gain, and this is a digital integral gain. So, this can be realized by a register, and we want to realize using MATLAB. I think we have already realized in the previous week how to realize this block level MATLAB implementation. So, one can write the transfer function, the whole transfer function as the VEZ in the z domain and VU of z, but we have also learned, if we want to delay this signal because we want to sample the signal at the edge of the clock that we want to customize, then the straight away if you write this transfer function in the MATLAB, it will be difficult to manage the edge. That means, it will compute at every 0 time, Ts time, 2 Ts time, like that. But suppose if you want to compute somewhere in between 0 to Ts time and we want to only update the controller. So, in order to do that, we have also learned how to use how to implement MATLAB block using difference equation. So this is a Z inverse block, and if you use this difference, you can also realize this using difference equation simply by plugging these three equations. You can difference equation that we have also learned. And this delay will be adjusted based on the clock edge, which will be used to update it, because this controller can also be implemented for varying time period, for variable frequency modulation also. That also you have learned. Okay. Now design of discrete time. So if you want to design then equivalent discrete time for a continuous time filter, that means Gs 1 by S plus A. Suppose if you, this is the continuous time filter that you want to design, which is a kind of low pass filter S plus A. Then how can we get its digital version? If you use the backward difference, we simply replace S equal to this term that we know, and there is a sampling time, so it will take this form. If you use forward difference, then we replace S equal to this, but this method is not recommended because it may lead to unstable system. That's why we are not writing the Z domain expression. Or you can use bilinear transformation, where you can get ZD of Z in terms of, you can simplify this expression. Now this bilinear transformation, when you get a Z domain transformation, that means if you know that which is called pole 0 mapping, it is Z equal to e to the power st. That is the exact mapping, and that comes from the fundamental Laplace transform theorem. That means if you go for how to obtain the transfer function using Laplace transform, and if you go to Z transform by two basic theorem, you can relate Z equal to e to the power st. But this is an irrational function. That means if you want to retain the logarithmic property, and this is an irrational transfer function, so you cannot actually plot it. So in order to get a rational transfer function, you need to approximate, and that is done by W domain, and this is simply similar to a bilinear transfer function, bilinear transformation, where Z, which is a irrational function of omega in continuous domain, can be converted into a rational transfer function of W domain, where W domain and omega are somewhat analogous. That means, when you say this omega, it is a continuous time frequency, continuous time frequency. When you say W, it is a transform domain from the Z transfer function. Okay. So we want to, and this is the inverse transformation also fine. We want to make sure how is the mapping. So if you take S plane j omega b a, this is the point that you want to map. So if you apply Z equal to e to the power st, where S equal to sigma plus j omega, then you can get this A coming to be here, then you can get B will be somewhere here, D will be here, then C will come here, like that. So it will be one-to-one mapping for the primary strip, and this strip is known as primary strip because it is valid from omega j omega s by 2 by minus j omega s by 2. Beyond that, there will be repetition. So within the primary strip there will be one-to-one mapping. Now when you go to W domain, from by using, I would say it is this is the Z equal to W domain, it is in the W domain. So in the W domain you will get almost similar, that means it can be shown more or less the W domain and the omega is the continuous time, they are more or less close, except for the problem of pre-warping problem, frequency warping problem, and that can be taken care by the frequency pre-warping. So in summary, the omega domain and W domain are somewhat analogous, where W domain is obtained from the Z domain by means of similar to a bilinear transformation, but it will introduce when you convert from Z to W domain, and if you want to, that means if you take a transfer function of GS and if you get GZ and then if you get GW, then between GS to GW you may get one extra 0 due to this sampling, that extra 0 will come at sampling frequency by 2. So that will introduce an additional 0 by means of a transformation, otherwise they will match more or less retain the property. So, in summary, we have discussed continuous time to discrete time transformation method, then we have discussed stability under various transformation method, and we have summarized the continuous time to discrete time transformation method, and we have learned that the back forward difference method should be avoided, otherwise a stable plan can become unstable in Z domain. And we have also learned that some implementation aspect, and what we learned, the forward difference is very easy, backward difference, and it is simplified, but it is somewhat conservative. Bilinear transformation is more accurate method, but it will increase the hardware complexity. So, in the subsequent lecture, we will learn that how to design a controller using this transformation method, and then finally we will also want to see using accurate discrete time model how to design, and we want to compare this design using transform domain and directly design in the Z domain. So, that is it for today. Thank you very much.